This webcast discusses how to finish the lab focused on energy transfer from gravitational potential energy to kinetic energy. And I'm going to pick up at Table 1 because in class we had gotten this far. Okay, so I'm starting with Table 1 where we recorded our data, and actually in class we made an Excel spreadsheet. And so I have that here now. Just to maybe review what we did here, let me make this a little bigger so it shows up better. We started the cart at different positions on the track, and we let the cart move down the inclined track, and we measured the velocity at the bottom, the maximum velocity. So for example, here is run 1, and the run started with I started recording data before the cart was moving. Then once the cart started moving down the track, the velocity increased very rapidly. Here's the maximum velocity that I've gotten the value for, and then when it hit the end stop, it bounced and stopped and would have stopped moving. So we have recorded that maximum velocity at the bottom in our table, have calculated the gravitational potential energy based on the height at that position, calculated the kinetic energy at the bottom of the track based on the velocity, and then we've calculated the difference between the gravitational potential energy, the EG, at the top, and the kinetic energy, the EK, at the bottom. Okay, so I think this table is done for most people, and so I'm going to just copy this table, and I'm going to put that into my report at Table 1. You could delete the table that's there. I think I may just paste it in there for the sake of time. Okay, so now we've got the data in the report. The next step is to put Figure 1, and Figure 1 is to show from Capstone the velocity versus time graphs for several initial positions of the cart on the ramp. So that is this graph that shows all of the runs, and so I'm going to snip that and just put a picture of this graph as Figure 1. Okay, and then just continuing here. The next step is, let's see, we've done these things. Oh, so we will need to show a sample calculation. We want to do that for anything. And so for gravitational potential energy, I'm going to do this for the first row of the table. And so the gravitational energy in that first row is the mass of the cart times g times its height. The mass of the cart was, I may be remembering this wrong, but I think we said 2555 kilograms. So 0.2555 kilograms times 9.8, and the height in the first row was 0.235 meters. And I would just multiply those together and fill in this number here, and that would be joules. This number should correspond to the 0.5883 that my table has. And so I think if I multiply these out, I would get 0.5883. You should actually multiply yours to confirm that. Okay, and then it says calculate the kinetic energy at the bottom of the ramp. And so I actually want to show that calculation, and that would just be that the kinetic energy is half of the mass of the cart times the velocity squared. And I just want to do this for the first row in the table to show that I can calculate it by hand, and I can get, see, the velocity was 1.58, that I can get the same value that my table has. Okay, so that's the purpose of these, is just to show that sample calculation. Okay, and then we want to do one of the percent differences. And so again, I'm just going to go to the first row of the table, 0.5883, 0.3189. And I'm going to calculate that, and I'll get the percent difference. Okay, so those are the sample calculations. Let's keep going here. Now I need figure 2. Figure 2 is the EG at the top of the ramp versus the velocity at the bottom of the ramp. And so that will be in Excel. And if you haven't already graphed this, I'm going to go back to just 100%. So I've got room to do the graph. But I want to highlight the numbers here in these two columns. The gravitational potential energy should be on the right-hand side. The velocity at the bottom should be on the left-hand side. When I've got those numbers highlighted, I'm just going to insert a scatter plot. Okay. And then we'll just get, so this is gravitational potential energy at the top of the ramp versus velocity at the bottom of the ramp. And we need some axis titles. Velocity will be on the horizontal axis, and I'm just going to say EG on the top, on the vertical axis. Okay. So looking at this graph, you might be tempted to say that this is linear, but I want to show you a different graph. This is for a different set of data, but is still gravitational potential energy versus the velocity at the bottom of a ramp. And you can see here that this data, which covers a greater range of values than we have, is clearly curved, and it's shaped like a parabola or a quadratic equation. And so I know that actually this data is not linear, and so we're going to linearize it. Okay, so I'm showing you this set of data so that you can see really what our curve should look like. If we had a longer track, we would have been able to get maybe a larger number of data points and would have had data that resembled more of a curve. Okay, so I'm going to first of all put this graph into my lab report. That's figure 2. Okay, and then below figure 2 it says, so based on the shape of the graph, what is the relationship that exists? And if you notice, it's just got some places for you to fill in some blanks. It's curved and resembles a parabola, where the parent equation is. So this is just the equation of a parabola, right? C is just some constant of proportionality. You know, it's just a shape factor, okay? But anyway, y is proportional to the x squared. So that means the gravitational potential energy at the top of the ramp is proportional to the square of the velocity at the bottom of the ramp. And we're going to use that understanding to linearize our data. Okay, so I'm going to go back to Excel, and I'm going to copy these two columns, just the columns that have the velocity and the gravitational potential energy. The cells in these columns both have formulas. Well, maybe the velocity doesn't, but the EG was calculated. So I don't want to paste, just do a simple Control V, go to the drop down under paste and say paste special, and click here where to just paste the values, okay? That will be important because we want to keep those numbers for the gravitational potential energy. Okay. Now, gravitational potential energy is not proportional to velocity. So I'm going to delete these velocities, and I'm going to change this header. Instead of saying velocity at the bottom, I'm going to say the square of the velocity at the bottom, and the units would be meter squared per second squared. Okay, let me make that a little wider. Okay, and I'm going to put a formula in here. You could calculate this by hand and type them in, but but we'll just put a formula so that it's easier to do. So you start with an equal sign, and then go up above and click in the cell that has the first value of the velocity. Come into the formula bar, do a Shift 6 to get the caret, and type a 2, because we are raising that velocity to the power of 2. You can hit enter. So 1.58 squared is 2.5. And now that I've got the formula, I can just copy it down. Go back into that cell where the formula is, bring your cursor to the lower right hand corner, hold the mouse down, and just drag it down the length of the table. Okay, so now I'm going to graph this, the gravitational potential energy versus the square of the, let's see, I can't see my insert. There we go. Versus the square of the velocity. And this now is linear. Okay, so this is gravitational potential energy versus the square of velocity. And I'm going to also put some axis titles. This is now the square of velocity. So that's meters per second squared. And then this is still EG, which is measured in joules. Uh-oh. There we go. Okay. For this graph, I need to put not only the graph, but also this table here in my lab report, because we need to have this table as evidence of, how we linearize the graph. Okay, so I'm just going to highlight the table and the graph and copy it, and then I'll place it here at figure 3 of the that didn't work well. Paste. Oh, I want an enhanced meta file. There we go. Okay. So now we need to find the slope of that linearized graph so that we can write a physics equation. And so I'm going to just do linear regression on this linearized graph. So I'll go to Data, Data Analysis, find the regression. First, I put in the gravitational potential energy cells because that's on the y-axis. Then I'll put in the square velocity because that's on the x-axis. I do want to get residual plots and line fit plots. I'll say OK. And here we go. Looks like a good fit. I've got a great R squared here of 0.9927. Here is my slope. So I'm going to highlight that so that it shows up well. And so I want to snip a picture of this to put in the lab report as evidence of the slope. Okay, and so that becomes figure 4. Okay, and then it says, okay, so what is the slope? And put some units on it. So my slope was 0.159. And if I go back and look at the graph again, I can see that, the units of the y-axis are joules, the units on the x-axis are meters per second squared. Okay, so I've got joules over meters squared per second squared. And if I wanted to write a physics equation, in this graph, the independent variable is the square of velocity. And so I'm going to represent that. I'm going to call that variable v for velocity squared. The dependent variable is the gravitational potential energy. Okay, so my gravitational potential energy equals there we go. I'm just ignoring the y-intercept. It's not real significant to what we're doing. Okay, so we've got a good physics equation. And how does this slope compare to the mass of the cart? Well, the mass of the cart was 0.2555 kilograms. This is 0.159. So it's clearly not exactly equal to the mass of the cart. Let me see what half of the mass of the cart is equal to. So 0.2555 divided by 2, I get 0.128. So I'm going to say the slope is similar to half of the cart's mass. Many times these slopes are related to something that we've held constant in the experiment, and this one I think is similar to half of the cart's mass. And so let's also look at the units. Let's see if we can simplify them. The slope had units of joules over meter squared over second squared. I know that a joule is a Newton multiplied by a meter. I know that a Newton is a kilogram multiplied by a meter per second squared. And let's see here if I can simplify. I'm getting messy stuff up here on the top. But I've got a meter times a meter per second squared. That's the same thing as a meter squared per second squared, right? And that's what I've got on the bottom. And so now these two terms can cancel each other. And so those units simplify to be units of kilograms, which are the units of mass, right? And so maybe it's not so, crazy to say that the slope is similar to half of the cart's mass, because the units of the slope are units of mass. Okay, so we're going to rewrite then our physics equation, and we're going to replace the numerical slope with the meaning. We said it meant half of the mass. And we're going to change EG to EK to recognize that the initial gravitational potential energy at the ramp was transferred to kinetic energy as it moved to the bottom of the ramp. If the track had been frictionless, which it wasn't, but if it had been, all of the gravitational energy would have redistributed to the kinetic energy storage mode. So basically, our original physics equation was, I don't remember the number, 0.159. But now I'm going to replace this with 1/2 of the mass, and I'm going to replace EG with EK. And so my new general model is going to be that the kinetic energy equals half of the mass multiplied by v squared, the velocity squared. And so this, we have, shown how that we could derive this equation as the equation to find the kinetic energy of the cart. Okay. In 31, it says, okay, but our track really was not frictionless. And so, can we, let's describe what was really happening. And then, and let's see. So I'm going to put the cart and the track and the earth in the system. Now at position A, we were holding the cart at the top of the track. And so all of the system's energy was stored as gravitational potential energy. When the cart got down to the bottom of the track, it was not really on the ground, right? I'm going to go back up and look here, but we saw that I'm sorry, I keep having to move something so I can see. But we saw that because this little foot here, that on this end of the track, that really it was 8.4 centimeters above the table, even at the bottom of the track. And so there's still a little gravitational potential energy there. So let's go show that. Come on down. Okay, so there's still going to be a little gravitational potential energy. Not as much as there was at the top of the track, but some. But also, the cart was moving, so there's some kinetic energy. And, there was friction, because, in real life, there probably was some friction. And so, this is really more of the situation that we had, where the gravitational potential energy that existed at the top of the track equals the gravitational potential energy at the bottom of the track plus the change that we saw in the kinetic energy plus however much energy was dissipated. And then 32 says, let's use this conservation energy equation and the data from run 1, that's the top row of our table, and find the value of the coefficient of kinetic friction. Okay, so I'm going to leave this for you to do, except that I'll just say that, we're going to say this is the height at the top of the ramp. This is the height at the bottom of the ramp. The velocity is listed in our table. And the dissipated energy would be the friction force times the path length. Well, the friction force is the coefficient of kinetic friction times the normal force times, and the path length here is 80 centimeters. We're going to have to convert that to meters. You're going to have to do a little bit of a force diagram because the cart, you need to find the normal force on that cart, right? It's perpendicular to the track, and you're going to need to find that so that you can calculate the friction force. And then the thing that we'll be solving for is this, because that's what it's asking for. It's asking us, what is that kinetic coefficient of friction between the cart and that aluminum track? Okay, let's see what else. Then in the conclusions, so we've got a I think I'm going to come to the conclusions in the next webcast and stop this one here. It's getting long.